Hello, welcome to episode 37 of the Stanford MLSys seminar series. My name is Dan. Today I have with me Fiodar, Piero, and our guest Chaoyang He. So before we get started, a reminder to subscribe to our channel, hit that like button, maybe click that bell to be notified when we go live. As always, our plan today is we're going to have a 35-minute talk followed by a podcast style discussion where you, the audience, can ask live questions. So this week we'll be discussing distributed machine learning and some federated learning with our guest Chaoyang He. A little bit about Chaoyang. He's a PhD candidate in CS at the University of at USC in LA. He's advised by a number of great professors out there. Before his life as a PhD, he worked at Tencent and Baidu and at Huawei, and is received a number of awards in academia, including the Amazon ML Fellowship, Qualcomm Fellowship, Tencent Outstanding Staff Award, among many others. So we're very excited to have Chaoyang here today, talking to us about some of his latest research. So with that, Chaoyang, take it away.
Okay, thanks for the introduction. I'm very happy to be here to introduce my research on distributed federated machine learning system for large-scale models. So today I will introduce two aspects of distributed ML system. One is dynamic distributed training for GPU cluster. Another aspect is about federated learning on some edge devices. So this is joint work with my advisors, Professor Matei and Professor Simon Westimher, who is also the director of the USC Amazon ML Center. So first, let's give you a high-level comparison of distributed training and the federated learning. As you may know, the main challenges of recent research on distributed training is that how we can accelerate the training of giant model like transformer models, which is based on attention-based mechanism, like the multi-head attention. Normally, we stack this simple architecture design into multiple layers, then we can scale up the model size into billion, even trillion number of parameters. By this way, normally we can improve the accuracy of many AI applications like latent language processing and the computer vision into a very high accuracy. So the key challenge is that how we can reduce the cost of training such giant model in this setting. Another setting is about federated learning, as you must know that which is quite different from the GPU cluster, that the edge device is resource constrained, and the connection between the cloud and edge device is very unstable and very limited bandwidth. So the challenge of these two and the goal of these two are quite different. In GPU cluster training, as you can see, our main goal is to train a large model in a reasonable training time and using reasonable edge cost and some hardware resources. But the goal in federated learning is to protect the data and model privacy, and also mitigate the difficulty of data centralization. You can imagine if there are many number of distributed data sets, how we can centralize data sets is very challenging. So not just about privacy. And the main challenges in the first part of distributed training is that from the system-wise, like communication cost and memory constraint and computational efficiency. But in federated learning, we mainly concerned about the data heterogeneity because each user may have different behaviors to generate different data sets. And also system heterogeneity is a very obvious properties in this setting. You can see some people use iOS, some other use Android smartphones. And also transversally is very important because sometimes we may see some malicious users may break the assumption of distributed optimization so that it can downgrade your performance of training. So in this talk, I mainly want to highlight three methodologies to handle this performance, these challenges. The first methodology is we should think about from dynamic system and the stochastic machine learning, which may lead to complicated interaction between multi-objectives. So the multi-objective means we may have objective improve the accuracy, efficiency, security, or privacy. So dynamic system here means the resource, for example, the GPU resource may be dynamic when you do training. And also the number of users may also be different in different phases of the training. So stochastic here means we may use different distributed optimizer, for example, add-on or federated optimization method. So which is quite complicated. We should think from the interaction of these two. The second methodology is about trade-off. As you may know that this is a very common methodologies in ML system research. We should think about how to balance different goals. And the third part, I think maybe we never talk about it in academia, but I think it's also very important. We should always focus on the key demand from different user cases. For example, some machine learning applications may have different goals. We can not always make everything perfect. We should just amplify one goal in these key applications, but not break the assumption of the other objectives. So in this talk, I will demonstrate these three methodologies with my recent papers like ICML pipe transformer and the trade-off in group knowledge transfer in Europe 2020, and also a best paper award FedML library and the ecosystem to show how to think from these three methodologies. So first, let's look at pipe transformer, which is a dynamic training system that co-designs the pipelining data parallelism and the training algorithm. So first, let's look at the motivation of this pipe transformer system. As I just mentioned, the system, the model size increased dramatically during in the past few years, especially the model size. You can see the GPT-3 has more than 100 billion level parameters, and recently speech transformer even enhanced the model size to 1 trillion level parameters. We can also predict that maybe later this year, people can propose more than 100 trillion parameters. However, the challenge is that training such large model, if you using one GPU, it may cost hundreds of thousands of GPU days. And if you train it many times, it may cost a lot of, even more than 1 year to finish the training. So that's why distributed training need to to solve this problem. And also, we can see when the model size become big, we cannot load the model into a single GPU's memory. So normally in distributed training, people normally use this kind of all reduced SGD, which just distribute the data set into different GPU workers, no matter it's located in different machines or in a single machine. And then we do all reduce to aggregate the gradient. So this is kind of data parallelism, which is very popular for distributed training before we have transformer. But after transformer coming, we can see that this is not enough. There are many two lines of work. The first line of work will be distributed system design and optimization. So here I summarize recent famous works by using these two dimensions. One dimension is that we can think from the data inter-batch and intra-batch. Another dimension is that we think from the model wise that we can split the model into inter-operator or intra-operator. You can imagine the operator as a layer. So for inter-operator, for example, the pipe dream, try to split multiple layers into a GPU and then to consider the interaction among different batches. So here is an example of a pipelining paradigm, which is used very frequently in training giant transformer models. So normally we cut the transformer layers into multiple GPU devices, for example, in device 0 to 3. And then we do forward propagation and do cross GPU communication among the forward propagation and calculate the loss. And then we do back propagation across different GPUs. But the issue of this problem is that the bubble size is too big. You can see that for specific device, if you think from the time scale, we can see that the bubble size is big. So normally we need to count the batch into multiple micro batches. So this is the idea of GPipe, a paper published in Europe. And so you can shrink the bubble size. We can also make this hybrid that we can combine the pipeline paradigm with data paradigm. So when it becomes hybrid, it means that when we finish the back propagation for specific layer, we can do all reduce with another copy in different machines. So AR here represents all reduce. Once we finish all the all reduce for different fraction of the layers, we can do update. So the update means we can call the optimizer to update the weight by using the synchronized gradient. So these are line work about pipeline and data parallelism. And also people try to propose different model parallelism, which means we just cut the layer into multiple GPUs inside the layer, not just the cross layer. So it's called intra-layer model parallelism. This is also a very important way to train giant transformer. And another line of work in AI community is that many published in AI-related conference like Triple AI, 3PI, Clear. So people are trying to shrink the size of the model, but keep the accuracy as the giant model. So the idea normally try to do sparse attention, neural-attached search to find optimal, efficient architecture, and also do sparse training, which we can pull in some connections, but keep the accuracy. And also we can think about how to design distributed training algorithm. But all this line of research are mainly focused on machine learning wise. It's mathematical kind of stuff that try to improve the accuracy and trade off the efficiency. So in this paper, we think differently. We are thinking that whether we can co-design ML and the system. So for example, on the left side, if you think about distributed training systems, they just view the ML and model and SGD optimization as black box. But the right side also has drawback, although it can improve the efficiency dramatically and mathematically, but the problem is that it lacks of system design to amplify the algorithm-wise advantage. So our idea is to combine these two. From the left side, from the system-wise, we consider the hybrid of pipelining and data parallelism, which is a popular method to train giant transformer model. Another side, we think about progress training, which is a dynamic training pattern. And then we can have idea about how to do elastic distributed training system. So the elastic distributed training system is inspired by 3 key observations. As you can see that in the, if we put the progress training method into, let's first look at the progress training. So progress training meaning that during the training, we can enlarge the number of layers or shrink the number of layers to join the training. For example, on the right side, there's a training method called progress stacking published in ICML 2019. So the idea is that during training in different iterations, we can use different number of layers to join the training. And on the left side, you can see the freeze training is also a similar concept, but in the opposite way, that we shrink the number of sites and we freeze gradually during training. For example, we can train 12 layers at the beginning, and then we shrink it to 4 layers and to 1 layer until the end. So all this, I call it progress training. There are multiple examples of this kind of training. So when we apply this kind of training into trade transformer, we find 3 key observations. One is that the computational cost becomes unbalanced. That's because you can see that when we freeze or some layers, or we add some layers, the workload of the pipeline will become unbalanced. Another problem is that memory may be reduced gradually, because when we don't need to train some layers, the forward and back propagations memory will be largely reduced, because when we don't need to do back propagation, meaning that we can reduce the cost for optimizer state, activation maps. So that's why the memory is also reduced if we apply to this complex system. And also the communication cost can be reduced, because when we freeze some layers, we don't need to synchronize the gradient. So it should be reduced gradually if we want to apply this system. So inspired by these 2 lines of work, we designed this pipe transformer to amplify the property of this progress training. So the idea is very interesting, is that we make the system dynamic and elastic. At the first beginning, as you can see, we have 2 machines. Each machine holds a pipe which has 8 GPUs, and they are connected by data parallelism. And after we freeze some layers, as the gray color shows, then we can shrink the pipe into 4 GPUs, because we don't need to do back propagation for these layers. So it requires much less memory cost. So that's why it can host by using 4 GPUs, but we have to rebalance the workload. So meaning that we have to define a workload balancer to redistribute the layer partition. And then we can see that some layers are released, so the GPU resource can become available for new computing. So here we just add some new layers to amplify the data parallelism, which can further accelerate the training a lot by using this mechanism. And also, if we freeze some layers, we can use some auto cache. This is not very local, but it's very useful in this setting, because when we freeze some layers in different time steps, we can reuse the output from the previous iteration. We don't need to do forward propagation for multiple times. So to introduce this idea with an animation, and here I show it using this simple case. We have a pipe in each cipher connected by DP. And once we shrink the pipes, we have some amplify release the GPU devices, and then we can add some blue colors here. So this represents new pipes, and they are connected by DP. So DP is a dynamic membership. We can join and quit from the DP. And then we can further shrink pipelines as the float number increase. And then we shrink the pipelines into two and add two additional layers, two additional pipelines, which can further accelerate the training and further shrink. And finally, you can find that it becomes true data parallelism. So this is a very interesting system operation that you can see shrink. We add more pipes and we shrinks, add more pipes, shrinks, add more pipes. So this is a dynamic system that's driven by the prograph training algorithm. It doesn't need to be phase training, but it can also be many other interesting algorithms that make the system dynamic. So, let me introduce some high-level ideas to do this system design. So we mainly use distributed APIs that's supported by PyTouch, including DDP, it's data distributed parallel, and also pipeline paradigm. And when we developed this idea, PyTouch does not support this pipeline paradigm. So we evaluate and test pipeline paradigm with this paper. And then we have this, then we define 4 components. One is freeze training algorithm, which can get some information from the training pipeline as indicator so that it understands how many layers should be freeze or should be frozen during the training, and it notified to the multi-pipe components. Then the multi-pipe component can decide whether to shrink the, for example, these 8 GPUs to 4 GPUs. If you decide to shrink, it will notify to AutoDP. And then AutoDP will try to create purple color pipelines here to amplify the partisan so that it can accelerate training. And also AutoDP needs to redistribute the data set into 2 subsets, because previously we only have 1 pipe, now we have 2. So each pipe should consume equal number of parameters, equal number of samples, but only but from the previous data set. So by this way, let me give you a high-level sense about the concrete experience result. As you can see, normally for distributed training, the throughput is stable. It's just a straight line during training. So throughput means samples number in the training can be consumed per second. So here you can see our system, the throughput of our system increased gradually during training as time goes. This benefit is obtained by our dynamic, as the animation shows here. So overall, it can accelerate training around 2.8 times. Since the training only evaluated on 2 machines, in our observation that it can accelerate more times speed up if we scale up to larger number of machines, which will be our future work. So due to the time limitation, today I only highlight this design. So for the source code, it's around 10K lines of source code. You can visit our website for details. And you can also get some technical details for these ideas in the other slides. So I will share your slides after this talk. So next, let's move. As you can also see that this idea can be extended to many other settings. An interesting setting that is about accelerating neural search, which is a very important direction like AutoML. We cannot search a large scale search space, but what we can do is to shrink the search space and search it gradually. So it can also apply to our pipe transformer system. So by this idea, I demonstrate how to think from the methodology of dynamic system and stochastic machine learning properties. So next, let's move to federated learning. I will show you how to do trade-off and on-demand. So federated is kind of widely interdisciplinary research, which is quite different from the distributed training on GPU cluster like the pipe transformer research. It has to consider the statistical challenges and also trustworthy like the robustly to adapt adversary attacks, and also system-wide efficiency and on resource constrained edge devices and many interesting applications. So currently federated learning is mainly is very popular, and many researchers in this ML conference try to tackle these challenges. And in our lab, we mainly focused on 3 kinds of research, including the ML-wise algorithm design, and system-wise, we want to try to think about how to reduce the system-wise cost, and also make it scale up to larger number of users. And also we are trying to do skill aggregation and make it resilient to malicious users. So in this talk, I mainly show you the ecosystem in our lab, which is called FedML.ai. It includes a FedML library, which I will introduce later, and the 3 levels of research. In the middle level is about the algorithm-wise research, try to address the problem I just introduced. And in the application level research, we mainly think about on-demand research in different applications because they may need to achieve different goals in different settings. And also we are thinking about developing the pipe transformer or FedML.ai infrastructure and system optimization to support so many algorithms and applications. And we are also doing review and revision papers to do field guide and point out the future directions. So first, let's check the paper FedGKT, which is the idea that I want to show you how to do trade-off in distributed ML system. So the goal of this research is to train large-scale models in edge devices, which is quite much more challenging than the training on GPU cluster for transformers. So here I mainly focus on CNN models. Like you can see a CVPR paper show that although we can use AutoML to shrink the model size only to 4 million parameters, but the problem is that the edge device is very limited. There's only limited memories, and we cannot directly load this giant model to do training because training normally requires 6 times larger memory cost. So the problem is that how to efficiently and effectively train such large model over resource-constrained devices. And such resource-constrained devices may have only limited memory and computation. There's no GPU accelerator, and also the bandwidth is very unstable and limited. So to give you a high-level sense, what is the challenge here, I just show you a basic concept of federated learning here. So in federated learning, at the first beginning, we normally broadcast the model to the client side. So the client side then can do training on local training to update the the model architecture. And then after the training, the client may send the way to the server side, so that you can do weight verification. And then after verification, the server will send the upgraded way to the client side. But the problem is that what if the W is a DNN? It's a deep neural network when the size is beyond the capability of the edge devices. So this is the key problem that we want to answer in this research. One related work called speed learning try to split the model into 2 portions. One portion is on the edge devices, another larger portion is on the server side. So for each mini batch training, we can do forward propagation, but pass through the intermediate representation to the server side. And server side do a forward propagation and then check and then forward back the intermediate representation to the client side, so the client side can calculate the loss. So by this way, it can largely reduce the communication cost because we only need to exchange the hidden vectors rather than a huge model to do synchronization. And also the client side is very efficient because we only need to hold a small fraction of the model architecture. But the problem that is very challenging is that this method cannot do periodical training like federated learning. Federated learning normally do periodical training, as I just showed here. We can train locally for many epochs and then synchronize to the server side. But this periodical properties does not exist in this speed learning because as I mentioned, each time we have to do forward propagation cross client and server side. So we are thinking about how to integrate this, the benefit of these 2 frameworks into a single one, which can be computation efficient, communication efficient, and the low communication frequency, like the federated learning, which has a local SGD there. So our idea is quite different from transfer data in centralized training that we transfer data to the center GPU cluster and do distributed training there. And also quite different from federated learning that need to transfer the model to the client from the client to the server. So we are thinking about how to transfer knowledge. So the idea is that how we can transfer knowledge from the research question is that how we can transfer knowledge from many small neural network to a larger one. If we can achieve this, meaning that we can train a powerful model on scattered edge devices which are resource constrained. So in order to achieve this, we propose a very concrete framework to demonstrate this concept. So first, we build based on speed learning, but we add the classifier based on the feature extractor on the edge devices. So by this way, we can train locally. And then the server side has a larger portion of the model, which can be accelerated by using GPU accelerator. So by this way, we can transfer knowledge by using the training result from the client side, like the yellow color is the hidden vector, hidden representation, and transmit the representation to the server side. So server side can use this representation as the X, and the Y is from the knowledge learned from the client side. So knowledge distillation on the server side will be directly use carrier divergence loss on the server side, so that we can transfer knowledge from many small neural networks to another neural network on the server side. And then the server side also need to transfer back the knowledge to the client side, because we can imagine that data set on the client side may not be enough, so that we cannot get good performance. By this transferring back, we can achieve higher accuracy for each client. So this high-level idea, we make it concrete by using alternative minimization. So we first formulate the client side as the optimization goal that learn a good feature extractor. On the server side, our goal is to find a great and larger classifier. And by this way, we can achieve lightweight training on edge devices, but intensive training on the server side, which can be mitigated by using GPU cluster. And we can also have 3 communication requirements, because the feature size normally is much, much smaller than the model size. So the loss function can be the distillation loss, which is very frequently used in log distillation literature. The idea is that we just output the logic, which is from the softmax layer, and plug into the carrier divergence loss. By this way, it can transfer logic from one neural network to another one. And then we can propose this learning framework. Essentially, it's based on alternative minimization, meaning that we can train locally on client side. We can also transfer logic to the server side and training many epochs. So it's alternative minimization problem, optimization trick here. And we further solve this problem by using distributed optimization method like local C with momenta. And we propose the idea of doing cross-round learning rate scatter. We find this method is much efficient, much effective than live distributed federated SGD. So with this learning framework, we can cut the ResNet into 2 portions and only put the few layers into the client side and load into, for example, the iPad and smartphones, and then put the large portion onto the GPU cluster to accelerate the training. So as you can imagine that this learning framework is quite different from fed averaging or distributed or reduced learning framework, as I mentioned in pipe transformer research. So here we need to upgrade the logic, the hidden representation from client side to the server side. So it's not just a weight or gradient upgrade synchronization. So and also another property of this learning algorithm is that it needs to train the model alternatively back and forth from the client to server and server to client. So as far as we know, there's no such a framework can search this kind of training flexibly, very flexible. So this motivates us to further develop FedML library, which aims at to support FedGKT like algorithm very productive and very efficient. So we don't need to consider too much complex design for the system and just focus on the mathematical formulation. So this is the high-level architecture of FedML library. In the low level, we have 2 key components. One is the distributed communication backend, which can support MPI, RPC, and MQTT for IoT device. And we make the communication layer abstract. By this way, we can exchange any information as we like. As the FedGKT shows, we need to exchange the hidden vectors, the logic. And on the right side, I want to highlight it, although the PyTorch can support the training on GPU cluster, but it cannot support efficient training on edge devices. So I think in the future, our community should focus on and think about how to design edge training engine for smartphones, which it does not have. So I want to make a placeholder to here so that in our future research can explore how to do it. And also, and based on this FedML core library, we can further do is to enhance the model size by to design new algorithm by using these two kinds of APIs, which just focus on mathematical formulation. And in FedML library, we also support model and data sets. You can directly use it for to explore your research idea. And in the high level, we have support different platforms and applications. So the key design here is the work-oriented programming interface, which is quite different from the interface in the left side. As you can see, normally when we do all reduced training, we just using the distributed APIs to do all reduced to synchronize with all other workers. But in federated learning, as I showcased with FedGKT, we need to pass different messages like logic and the hidden vectors. So we need to customize the message. So here, the work-oriented programming can support this very flexible. As you can see, you can add any kind of message payload as you like. And then also you can receive message from other clients. So it's programming from the workers-oriented, workers perspective. That's why we call it work-oriented programming interface. And we also designed the API with just 4 lines of code. You can create the device topology, load data, create model, and then call one line API to do distributed training. And we also support model trainer customization because, as we know, for different tasks, we need to customize the loss function and the optimizers. So we give the flexibility to users to do this. And so let's look at the benefit of FedGKT framework. It can achieve the similar accuracy. And the most significant benefit is that requires much less resource requirement on the Earth devices. You can see it requires 10 times less computational power on Earth devices and also requires much less communication than speed learning. So let's summarize the FedGKT research. As you can see here, it's the first work that tried to explore giant model on Earth devices for federated learning. And it's thinking from the knowledge transfer perspective rather than data on the model. So it becomes memory and computation efficient. And it also can train with the local SG matter like Federated to reduce the communication frequency. So it also reduces the communication bandwidth requirement because we only exchange the hidden features rather than entire model size. So there are some interesting directions for FedGKT is that how to make the hidden vector more privacy preserving and more secure to some malicious users. And we can also extend FedGKT to transformer models, which is very low harmful paper. We may need to try later to see whether it helps transform models. And another interesting direction would be, since we are doing knowledge transfer, we don't need to ask all clients to be the same architecture. So the architecture can be heterogeneous. Some guy use laptop, some guy use PC or smartphones. They can store different architectures. We can still do knowledge transfer because we use logic to synchronize the knowledge transfer. We don't need to be the same architecture. This can be a very interesting future direction. So the long-term goal of FedGKT can be, we also think about how to do knowledge transfer in IoT or 5G setting. We want to transfer knowledge from multiple clients to a centralized server model. So by using this group knowledge transfer, I showcase how to do trade-off for distributed ML system among multiple objectives. In group knowledge transfer, I showcase the to trade-off between communication and computation cost and also guarantee the accuracy. So next, let me show you how to do ML research on-demand perspective. So as you can see that in order to achieve this goal, we developed a FedML ecosystem, which mainly focused on the application level. We want to achieve this because we think that each scenario, each user case should have 3 different goals, different objectives to serve its customers. It doesn't need to be universal solutions. It cannot be. For example, if you use Federated, maybe it cannot solve your problem in NLP domain. So to achieve this, we propose FedNLP framework in FedML, which can support many advanced tasks like reading comprehension, question answering, and many interesting NLP tasks that have never been used in federated learning. And we integrate image segmentation, which is for medical setting, and object detection for autonomous driving, which are very interesting applications for these scenarios. And we also think about, for example, the AlphaFold tool, which is very famous research recently published by DeepMind. that we want to do some molecular ML in federated setting. This is motivated that many factories, for example, drug discovery factory, they can share some experience results and share some labels, chemistry labels, without disclosing their commercial benefits. And we also think about IoT, because IoT is very important because of the security. We can use federated learning to detect some abnormal data sets. So this is very promising directions. So all these kind of research, all these FedML related ecosystem are published in fedml.ai. So you can find these related papers to see, to try some new ideas based on our framework. So, so here I want to highlight the third methodologies I mentioned here, as that if we think from the ecosystem application level, we can always find that different use cases may have different demands. So that's why I prefer to do this kind of methodology, just to focus on the key demand rather than to make everything perfect, which is normally impossible for complex optimization problem. So finally, let me briefly introduce our research in trustworthy AI, which is USC Amazon Center, sponsored by Amazon Annex AI. So in this center, we mainly do research in federated learning and also consider research about pipe transformer-like research, distributed ML. So you can find our research on these two, in these two websites, I think, distributed ML and fedml.ai. So I hope you can get a sense about these three methodology of distributed ML system. I hope these three use case can inspire you to propose more research ideas in these three directions. Okay, that's my talk today.
Cool. Thank you so much. Thanks for that talk. It was really great. So now, as you know, we're going to transition into the Q&A section. So as a reminder to the audience, please, send in questions via the YouTube live chat. And, as we do every week, we'll look at those, aggregate them, and ask them to Chaoyang. I see we already have a few comments in the chat, but you can continue posting questions, and we'll get them across. So just to kind of get us started, one of the things I was kind of wondering about in your talk, so you talked about, this great work in kind of distributed ML and adapting it to kind of some of the newer architectures that we were seeing, like transformers, especially, as they get bigger and bigger. And you also talked about this nice work in getting, bigger models than what you might traditionally see on a phone, but kind of more traditional models like ResNets running in a federated setting. I wonder, do you think we'll ever be at a place where you can kind of distribute something like training a giant model with billions of parameters or trillions of parameters potentially, like GPT-10 or whatever? Do you think we'll ever be in a place where you could see that training in a federated setting, kind of training in a very distributed way over edge devices?
Oh yeah, this is a very interesting discussion that we already have previously. So you can imagine that in the future, we may have a billion number of users. The data set is big enough to train, for example, GPT-10, as you mentioned, in the future. But the problem is that how we can scale up to such large number of users. So this may be the key challenge here. And we can also think from another angle, which I think is much more practical in current distributed training system. We can think about the pre-training in federated learning setting. For example, we can pre-train a giant GPT-3 in the distributed cluster using pipe transformer, for example. Once we get the weight of this giant GPT-3 model, we can directly download into the federated learning setting. What we do is just do fine tuning. Fine tuning means that it adjusts the weight using the private data set owned by the user. And by this way, we don't need to train in thousands of epochs, many thousands of GPU days. Maybe you just fine tune locally for a few iterations, but still in a collaborative fashion. So this way, the main bottleneck is not the longer training time. The main bottleneck becomes how we can train this giant model in memory resource constraint. For example, the GPT-3 may not be loaded into the smartphones because of memory constraint. So we may also need to do some offloading or some frozen algorithm as I introduced in pipe transformer. You may need to freeze some backbones and only fine-tune a classifier which has fewer number of parameters. So we can define some adaptive algorithm that can load into different resource in user side. So by this way, I think it's practical, and we are also doing some demos in FedML, try to see what's the performance if we fine-tune a giant GPT-3 in, currently we are not using GPT-3, we are just using BERT, for example, and to see whether we can improve the accuracy using private data sets. I think these are two promising directions.
Cool, thank you so much.
Yeah, great question.
As a follow-up to that, Chaoyang, I actually have a question that is like a little bit a technical detail that I was curious about from, in particular, the second part of the talk, the federated learning piece. Mm-hmm. If I understand correctly, the different features extractors from the different edge devices, they are kind of independent of each other. Do you understand it correctly? And so basically they are, trained. So because those representations are they used to match, then the logics of the final model, the server model, but there's no other constraints than that, right? That's the only constraints that keep them together to a certain extent. They're not communicating to each other. Am I correct with that?
Yeah, I think you understand correct that we don't need to consider how to align the feature from two clients. Mm-hmm. So align feature, for example, if you do pooling in model compression, you don't need to align the masking if you want to do aggregation, right? But here we don't need to do such kind of techniques because we directly ask the server model to train based on a specific client's feature. And after this training, another client comes, right? It can continue the training. So to synchronize training on the server side. The server does not aggregate all the feature from client and then training. We just first come, first serve in server side.
Right. Yeah. What have you observed with respect to these features extractors? Do they converge to something similar, or are they really different from each other? What have you observed?
You mean the training curves?
No, I mean for instance, given the same input, would they provide the same representations, similar representations, or very different representations?
I see. So you mean after the oscillatory minimization, so what the representation for specific client, whether it's the same with other client? Yeah, we do check this. We can calculate the similarity score, which is similar like the pipe transformer, the freeze training of them. We find that they have different patterns here. But the classifier ability is to learn to try to classify different representations. Mm-hmm. So it can be viewed as the personalized federated measure in terms of the representation because each client has different feature. So the feature extractor will be different, but the classifier will be boost performance by the server side because classifier is very weak on the edge device. If you borrow the logic from the server side, the giant model which observe all the logic from all the representation training from all the client. So finally, the model will become a combination of the feature extractor and the larger portion model on the server side. So although the feature extractor is different, but the classifier had the ability to classify different features from clients. So that's why, although a specific client does not have enough data, finally you can get a very powerful model by borrow knowledge from other clients.
Got it. That's very interesting. Thank you for your answer.
I was actually kind of wondering, how do you think about the privacy goals of federated learning when you're transferring, knowledge or these intermediate representations from the edge to centralized servers? Because I imagine, you don't want to be sending raw data.
Yeah.
That's one of the reasons why we do federated learning. But then if we start thinking about, certain representations of that raw data, are we still respecting kind of privacy goals, or are those maybe, is there some kind of proof to talk about there, or what do you think?
Yeah, so currently there's no such a mathematical proof to demonstrate whether it's more secure than others, but we do check this by thinking from two directions. One is to do skew aggregation. Skew aggregation is very similar to do skew aggregation for model aggregation. So for example, you have a way to do skew aggregation on the server side. So server does not know specific users model architecture. So here, You can also view this tensor, this hidden representation, as a kind of model architecture and do skew aggregation. Skew aggregation means that we add mask into this tensor, and the server does not know a specific user's tensor, but it knows the sum of the tensor. So this is the kind of direction we are doing in our lab. We do actually we do have a paper that submit to Europe to solve this problem. Another direction we are thinking about to make the layer adaptive. For example, you currently in Federated we only have, for example, 3 layers on Earth devices. For example, maybe different client has different number of layers. Once making it heterogeneous, it becomes very difficult for attackers to reverse the knowledge from this hidden representation, because they are from different number of layers. If they're from the same number of layers, you can get some catcher and then you can reverse it, right? So these are 2 directions that we think we can make the attack more difficult for.
Yeah, it's like making a longer password, or adding numbers and special characters.
Yeah, exactly.
Very cool.
Yeah. These are 2 we are trying.
Hey Chaoyang, so I'm reading some of the comments that are coming in, and one of them from Ian Timmis, he points out that it's kind of strange that the major libraries like PyTorch and TensorFlow don't really support mobile training or federated training kind of out of the box. One of the concepts that we've talked about a lot in the seminar has been about things like hardware lotteries or software lotteries. What role do you think that plays in kind of like deploying some of these federated algorithms? Do you see where do you see kind of an end goal in terms of how easy it would be for somebody to deploy a federated algorithm in whatever setting they care about?
Oh yeah, this is a very practical question actually. Although we have a lot of research results in academia, but currently I don't think there's one solution that can make this federated learning system practical. So that's why I'm thinking from FedML.ai ecosystem. So in the future, I'm very interested in develop an ERG engine, which is debuggable and support some AutoML techniques. You can imagine if you want to turn hyperparameters on Earth devices, every time you have to launch a large number of clients and help you to try different hyperparameters. It's not the same as you try in a distributed cluster. You can always keep the machine there or use some batching job scheduler and to ask different GPUs to train. But in federated learning setting, this hyperparameter turning is very difficult. So I think hyperparameter optimization is very important. Such kind of optimization techniques is very important for this ERG training engine. So it should support some remote debugging and remote hyperparameter optimization. So currently, I don't see such an engine support this. So maybe in the future, for example, PyTorch Mobile and TensorFlow Federated should support such kind of techniques to improve the efficiency of hyperparameter turning. And another angle, I think, is that how to reduce the cost on the Earth devices and how to reduce the complexity of the heterogeneity on Earth devices. You can see different users, some use laptops, some use PC and smartphones, and they have different hardware capacity. So we cannot directly deploy one model architecture to the Earth devices. So how we can develop an engine that can make the resource constraint problem solved and make the system adaptive. For example, we have multiple selections for users. Once we find a specific resource constraint, we can only select one model architecture. But the problem will be that how we can aggregate the model if the model architecture are different from different users. This will be very challenging. We directly do model aggregation. We need to think about how to do heterogeneous aggregation. So I think the ERG engine on the smartphones not only there, but also need a sorry. Hello, I cannot hear. I cannot hear.
Yeah, I think.
Hello.
So Chaoyang, I feel an issue with the microphone.
So the issue.
Like anytime someone talks.
What's wrong? So maybe let me And
Can you hear me correctly?
yeah. Hello.
Chaoyang, this
Hello. Can you hear me?
Okay,
All
that's
right.
better.
Okay,
It's
cool.
very noisy in my side. I don't know what's happened.
very sorry about this. I think we solved it now.
Yeah.
Okay.
All right. Cool. That was F's in the chat, folks. I think we are back. Right.
So in short, my answer is that for your question, my answer is that we should have a Earth training engine, but supported by the cloud, so we can do some remote control.
Now, speaking of, so Dan mentioned things like hardware lotteries, and I want to talk a little bit about pipe transformers. You know, the first thing you chatted about. Do you think that the hardware, like current generation of GPUs, does a good job supporting dynamic training algorithms? And just to tie in a question from the audience, something like pipe transformer, how many GPUs does it take for you to start seeing benefits from it? Is it effective in, say, a cluster as small as 8 or 10 GPUs, or do you think you need hundreds before pipe transformer makes sense to be using?
Okay, thanks for your questions. Can I share my screen? I think for this question, I need to use some animation.
Yeah, go for it.
Okay. So in pipe transformer, actually, when we published the ICML paper, we only used 2 machines. But recently, we began to scale up in AWS AI to see whether it can support larger number of GPUs. So let me show you the figure here. Yeah, so in this figure, as you can see, we only use 2 machines. We can see the benefit. Actually, in our paper, we discuss this, that if you only have 1 machine, you can also have the enjoying the benefit of pipe transformer, because if there's no 2 machines, we can also shrink the pipes. You can see here only one GPU server, but we can also add another pipe. So final phase for a single machine can be like this, right? So you can also enjoy the benefit of enlarging the parallelism by adding more GPUs. More pipelines. And if you use even more number of GPUs in a single server, the bandwidth become larger, because you can imagine if you have 16 GPUs, the increase of the parallelism becomes 4 times and even 16 times, right? And in the later phase, and I mean the data parallelism. So another angle to improve it, maybe we can do cross machine pipelines. So currently it's constrained by the infrastructure. We don't have such a cross machine, but we are still doing it. We try to do RPC. So RPC is a kind of way that we can call remotely and transmit the tensor to another machine. But the issue here is that we need to consider tensor-aware RPC. We cannot directly move the memory from GPU to CPU and CPU synchronize to another machine and then downgrade to the GPU memory, which will cost a lot of time. So we hope we can do GPU direct. Once we have GPU direct, we can consider cross-machine pipe transformer.
I see. So that might inform kind of next generation GPU design or DGX machine design, perhaps.
Yeah, and as for your another question, you said that whether the infra can support the dynamic system. I think it's easy, because you can see we can have different active group. So progress group means that we can have training group and idle process group, and we can do communication between these 2 groups. So I think PyTorch and TensorFlow similar frameworks, they already support such kind of progress group techniques. So this kind of API is easy to use to make the system dynamic. And as for the pipeline dynamic is also easy, as you can see from these APIs. So this is the API from PyTouch. In this API, we can define the model and chunk number. So every time you want to shrink or enlarge the pipe, make it elastic, you just delete the instance and create the instance. So in our paper, we showed the time to uninstall and install this instance, which cost only less than 100 milliseconds. So you can imagine this, if it's less than 1 second, it's very limited time. So it's very trivial in a large scale training system, which normally costs hours of training. Yeah.
Got it. Thanks.
That's my question.
Yeah, I think I can ask like maybe one few last question from the audience. People were really interested in pipe transformer. Some of them asked if there are like constraints about the number of machines that it's supposed to work on, if it works on smaller number of machines, bigger number of machines, and other ones asked about if it's something that is the algorithm is something that is limited to transformer architectures, or could we think about ways to use it also for other kinds of architectures in the future?
Oh, thanks for the question. So the first one, I think I just already answered that even we use just one machine, which has multiple GPUs, we can also scale up and down, and we can also add some data parallel workers, add more pipes, so to enjoy the benefit. But the benefit may not be so large as the multiple machine settings. And for the second question, I think is that so what's your question? Sorry.
Yeah, so the question was if we can apply the same principles also for other architectures.
Oh, yeah. I think our idea is does not require a specific architecture as long as we can partition the model into multiple fractions and assign into different GPUs and construct the pipeline. I think it is feasible if the model architecture can be done like this. But I think we need fine-grained design, because for different model architecture, normally when we use different load balancer to partition it, we need to consider the trade-off between the communication and the computation. For example, if you balance the parameters in different GPUs, maybe the communication cost will become the bottleneck, because the way you partition, maybe the hidden vector is very large, right? But in order to reduce the communication, you need to make the parameter size unbalanced. So although it's agnostic to the model architecture, but I think the partition part should be fine-grained design. We do have a load balance over them. Currently, we just use mean and variance. We calculate the mean and the variance to do the partition. So if we apply to different model architecture, for example, ResNet is a similar architecture as transformer, which has very uniform layers, just stacking multiple layers. If this is the case, it can easily be applied. If for other architecture, which is very fancy, for example, if you cut from the middle, the trade-off becomes very complex. We may need to design algorithm to handle this.
Got it. Thank you very much.
Cool. Well, I think we are, approaching kind of the end of the hour. So sorry about that little technical hiccup in the middle. So it's been a great talk, great conversation. So I want to thank you, Chaoyang, for coming on. I also want to thank our internet audience. It was a lively discussion today. I asked some really great questions. As always, you can go to our website mlsys.stanford.edu to check out our future schedule. And find our mailing list. We only send out I think it's 2 emails a week. So we promise no spam. If you're watching on YouTube, subscribe to the channel, smash that like button, hit the bell icon to get notified when we go live. We promise, great content for many weeks and months to come. Next week, we're very excited to have Priyan Jamshidi on. He'll be talking about causal analysis in ML. So with that, we can wave goodbye to the internet audience and see everyone next week.
Bye-bye.